Hi guys, myself E. Ramsesachari from CSSE section. In this video, we will learn about automata modular theories. Topics: Introduction, Automata theory, Applications of automata theory, Conclusion. Introduction: Automata theory is an existing theoretical branch of computer science. It established its roots during 20th century as mathematicians began developing both theoretical and literally machines which imitated certain features of man, completing calculations more quickly and reliably. The word automation itself, closely related to the word automation, denotes automatic process carrying out the production of specific process. Simply stated, automata theory deals with the logic of computation with respect to simple machines referred to as automata. Through automata, computer scientists are able to understand how machines compute functions and solve problems. More importantly, what it means for a function to be defined as computable or a quotient to be described as decidable. Automats are abstract models of machines that perform computations on an input by moving through a series of states or configurations. At each state of computation, a transition function determines the next configuration on the basis of a finite portion of present configuration. As a result, once the computation reaches the accepting configuration, it accepts that input. The most general and powerful automata is the Turing machine. The major objective of automata theory is to develop methods by which computer scientists can describe and analyze the dynamic behavior of discrete systems in which signals are sampled periodically. The behavior of these discrete systems is determined by the way that the system is constructed from storage and combinational elements. Characteristics of such machines includes input, assumed to be a sequence of symbols selected from a finite of input symbols, namely set is the set where k is the number of inputs. Output, sequence of symbols selected from a finite set of z, namely y1, y2, so on yn, where m is the number of outputs. Sequence of symbols selected from. There are four families of automata: finite machine, push down automata, linear bounded automata, Turing machine. The families of automata above can be interpreted in a hierarchical form, where the finite state machine is the simplest automata and the Turing machine is the most complex. The focus of this project is on the finite state machine and Turing machine. A Turing machine is a finite state machine, yet the inverse is not true. Let us discuss about finite state machines. The existing history of how finite automata become a branch of computer science illustrates its wide range of applications. The first people to consider the concepts of finite machine include a team of biological scientists, mathematicians, engineers, and some of the first computer scientists. They all shared an interest to model the human thoughts process, whether in the brain or in a computer. A logical calculus nervous activity made significant contributions to the study of numerical network theory, theory of automata, the theory of computation, and cybernetics. Later, two computer scientists D.H. Mealy and E.F. Morey generalized the theory to much more powerful machines in a separated papers published in 1955 to 1956. The finite state machines that Mealy machine and Morley machine are named in recognition of their work. While the Mealy machine determines its outputs through the current state and the input, the Morley machine's output is based on upon the current state alone. An automaton is which the state set q contains only a finite number of elements is called as finite state machine, FSM. The finite state machines are abstract machines consisting of a set of elements, set Q, set of input events, set I, and a set of output events, set Z, and a state transition function. The state transition function takes the current state and an input event and returns the new state of output events and the next state. Therefore, it can be seen as a function which maps an ordered sequence of inputs events into a corresponding sequence or set of output events. State transition function I tends to Z. Finite state machines are ideal computation models for a small amount of memory and do not maintain memory. These mathematical models of machine can only reach a finite number of states and transitions between these states. It means application is in mathematical problem analysis. Finite machines are also proposed aside from general combinations such as to recognize regular languages. In order to fully understand conceptually a finite state machine, consider an analog to an evaluator. An evaluator is a mechanism that does not remember all previous requests from service, but the current flow, the direction, motion, and the collection of non-eight satisfied requests. An evaluator is operated would be defined by the following method terms: states, finite set of states to reflect the past history of the customer's request. Input, finite set of input depending on the number of floors where the evaluator is able to access. We can use the set I, whose size is number of floors and in the buildings. Outputs, finite set of output depending on the need for the evaluator to go up or down according to the customer needs. A finite state machine is formally defined as a pi tuples Qij delta W, such that Q means finite state of states, I means finite state of input symbols, Z means finite state of output symbols, delta means mapping I and Q called transition function, W means mapping W onto Z called output function. A is set of states where F is a subset of Q. An example given in the below diagram. There exist several types of finite machines. They are acceptors, recognizers, transistors. Acceptors either accept the input or do not. Recognizers either recognize the input or not. Transistors generates output from each given input. Applications of finite are found in various of subjects. They can be operate on languages with a finite of words. Various types of trees and in hardware circuits where the input and output are byte vectors of a fixed size. While an automation is called as finite, its most symbols are used below. A Turing machine is formally defined as the set of Q sigma delta gamma Q naught BF, where delta means then next to move function, Q means finite state of input and output symbols, delta is set of including B symbols, etc. Applications: fluid flow, snowflake and crystal formation, choice theory, cosmology, financial analysis. Conclusion: therefore, the major difference between a Turing machine and two-way finite automata lies in the fact that Turing machine is capable of changing symbols on its shape and computer execution and storage. For this reason, it can be said as Turing machine has the power model all computations that can be calculated today. Truly modern computers. Thank you.